moment generating functions. I love this. Love me some moment generating functions. So recall, first of all, if x is a discrete random variable, then its moment generating function, which maybe we'll denote with little m, I think your book does too, little m of x t, this thing is defined to be the expected value of e to the t x. Okay, this is the moment generating function, and this guy exists. We say that it exists if it is finite on some interval around 0. Okay. Actually, this is in general. This is in general. This is yeah. I'm gonna get rid of that. There we go. That's the moment generating function for a random variable. Now let's think about the discrete or continuous cases. So we'll have if it's discrete, then this is what does this guy look like? It's going to be a sum, right? E to the tk times the probability that x equals k if x is discrete. And otherwise, it's going to be the integral e to the tx weighted against the density function for x dx if x is continuous. And also remember, we also have those mixed random variables to consider, right? With sort of discrete parts and continuous parts. If you have that case, and we probably won't do any of that, but if we wanted to, it would just look like this, right? Weighted against the differential of the CDF, right? If x is mixed, okay? All right, so here's a theorem for you. Theorem. Moment generating functions uniquely determine distributions. That's when they exist, that is, of course, when they exist. Okay, pretty much the ones that we consider will all be okay. All right, nothing to worry about that. What we mean by this is that is if I have two random variables x and y, x is equal in distribution to y, meaning it has the same distribution, has the same probability density function, has the same behavior as y. This is true if and only if the moment generating function for x equals the moment generating function for y for all t. Okay. Let's do an example. So let's say that maybe you've seen something like this before. Suppose x1, x2, etc. up to xn are independent exponential lambda random variables, meaning that the mean of each one is 1 over lambda. That's what I mean by that. Then what's the distribution of the sum? How does that behave? well, I already know. I think we've talked about this. The sum of independent and identically distributed exponential random variables is gamma, right? Yeah, and we can show this using moment generating functions, because here the moment generating function for the sum of those guys and girls, this is just the expected value, right, of e to the t times that sum. I goes from 1 to n. Now, this is expected value of the product, right, of e to the t xi. I goes from 1 to n, like that. Now, these are independent, these x's. So all of these are independent too. All these e to the t x's are independent. Okay, and so if I have the expected value of a product of independent things, remember that's equal to the product of the expected values, right? So I'm taking this step by independence of the xi's. But all of these things have the same distribution. So that means all these means are the same. All of these expectations are the same. Same. So, in fact, I can just say it like this. It's the expected value of e to the t x 1. I can, choose the first one, or the nth one, or the second one, or whatever. Raise that guy to the nth power. All right. And so now I know that x1 has an exponential distribution. And so I know that the moment generating function for an exponential, I already know this. This is going to be, 1 over 1 minus t over lambda, right? Just raise that guy to the nth power. But I recognize this if you look in the back of your book or somewhere in a table of moment generating functions online or wherever. You'll find that this is, in fact, exactly the form for the moment generating function for a gamma, right? Yeah.